Hello everyone, today we'll be preparing and standardizing a sodium hydroxide solution with potassium hydrogen phthalate. I need this for standardizing acids as a part of the zinc plating Masterclass series. However, this procedure is a standalone method. You can use this for any application that you may need. We'll start by dissolving sodium hydroxide solids in deionized water for our base solution. Then we'll standardize it using two titration methods. First, an indicator-based titration, then a potentiometric titration with a pH meter for higher accuracy. Titration is a process where the concentration of a solution is determined by reacting it with another solution of a known concentration. In our case, sodium hydroxide is a strong base. We'll be titrating it against potassium hydrogen phthalate, which is a weak acid. The problem with sodium hydroxide is it aggressively absorbs moisture and carbon dioxide from the air. So even if we carefully weigh it, the resulting solution will not have the expected concentration. Potassium hydrogen phthalate, on the other hand, is far more stable. So an accurately weighed amount will produce a reliable solution concentration. If you'd like to follow along, the detailed procedure and record sheet is in the video description. You'll find both a printable PDF and a spreadsheet that will do most of the calculations. All the sources for this process will also be there as well. I recommend wearing eye protection and gloves at the very minimum. Here's everything that we'll be using. Let's get started. I start by boiling distilled water. This removes dissolved CO2 and other gases. Then I pour the hot water into capped glass bottles for cooling. I boiled about 2 liters. Because the sodium hydroxide I had was in flakes, I had to crush it into a powder with a mortar and pestle. I weighed out about 4 grams of sodium hydroxide as accurately as possible. My exact mass was 4.02, so I took note of that. I rinsed out a 1 liter volumetric flask. Then I added the sodium hydroxide solids to it along with the still warm boiled distilled water. The warm water really helped quickly dissolve the sodium hydroxide solids. Normally it takes a lot longer. I weighed the empty HDPE bottle that I'd be using for the sodium hydroxide solution before and after I added the solution. This will allow me to make molarity adjustments if I want. Since I know the exact volume and the corresponding mass, I can make adjustments in the future. I actually made a mistake here. I should have first put on the label, then taken the mass. Because of this, at the end, after adding the label, I had to weigh it again to account for the label's mass. Now I'm preparing the potassium hydrogen phthalate solution. I started by weighing 10.221 grams of potassium hydrogen phthalate. The actual mass that I had was 10.22. Unfortunately, my scale is not accurate enough to get the third decimal place. I only have 2 decimal places, and the second decimal place is pretty uncertain anyway. So that's why I'm using such a large amount in the 10 gram range, so I can be sure that my mass is relatively accurate. The smaller the mass in this case, the less accurate and less confident I would be. I dissolved the potassium hydrogen phthalate in a 500 milliliter volumetric flask using the boiled distilled water. Again, the warm water really helped. I also transferred the potassium hydrogen phthalate solution into a HDPE bottle. I did not take the mass as I would not be adjusting the molarity of this solution. I set up a burette and rinsed it out several times with distilled water. Then I rinsed it out with the sodium hydroxide solution that we would be using. Then I filled the burette up with the sodium hydroxide solution way past the 0 mark. While the bubbles were settling, I poured exactly 20 milliliters of the potassium hydrogen phthalate solution. I transferred the potassium hydrogen phthalate solution to a 250 ml Erlenmeyer flask. I then diluted it to about 150 mLs. I then added 1 to 2 drops of phenolphthalein indicator solution. I made this solution in a previous video, check the description. Now that the bubbles had settled, I fully opened the stopcock to flush any of the air at the tip. Because we are fairly confident of the sodium hydroxide solution concentration, I began the titration by adding 15 milliliters of the sodium hydroxide solution to the potassium hydrogen phthalate solution. As you can see, the pink color is developing locally, but then quickly dissipating. As the titration proceeds, the pink takes longer and longer to dissipate. This is due to reaction rates. Once I passed 15 milliliters, I was a lot slower with the titration. As you see, when we've reached the endpoint, the pink color persists and does not dissipate. However, I do think I overshot it a little bit because I was letting it drip into the Erlenmeyer flask and my hand wasn't in the right position to turn the stopcock off immediately. However, this doesn't matter for our application as we're using this endpoint as a gauge for the potentiometric titration. If you'd like to get a more accurate result, repeat this process 3 or 4 times and average the results. Now I've set up the bench for the potentiometric titration. I have a stir plate, pH meter and probes, and the calibration fluids. I started by rinsing off the probes and calibrating the pH meter. The pH meter has to be calibrated prior to use. 3-point calibration may not be necessary before this, but it's what I did. I believe a 1 or 2-point calibration is the minimum for the pH meter prior to a titration procedure. Once the calibration was complete, I positioned the magnetic stir, burette, pH meter and probe, and beaker all so we can comfortably perform the titration. I added exactly 20 milliliters of the potassium hydrogen phthalate solution to the beaker. Then I diluted that to about 150 mLs. This way the pH meter probes will stay submerged. I turned on the magnetic stir at a gentle pace and made sure that there was no interference with the pH probes. Then, when the pH reading stabilized, I took note of the pH level as my initial reading. I proceeded to titrate in 1 milliliter increments. And sometimes I overshot a little bit, sometimes I undershot a little bit. It's not too important. As long as you take note of the exact volume and pH, we can construct the curve. I did do a fine step interval, 3 milliliters before and after the estimated endpoint. So from the indicator titration, we knew that the endpoint was at about 20 milliliters. So at 17, I started taking readings at 0.1 milliliters all the way to 23 milliliters. Of course, it is not always possible to exactly dispense 0.1 milliliters. In some cases, I went 0.2, 0.3. In some cases, I did dispense exactly 1 milliliter. As long as you take note of the exact volume and pH, there is no worries. The titration gets quite exciting near the endpoint as the pH changes really rapidly. Now that we've gathered all the data from the lab, we can proceed to calculate our experimentally determined molarity. Before we begin, there's a few things worth mentioning. First, you don't have to manually perform the calculations. This spreadsheet automatically calculates the values for the indicator titration. For the potentiometric titration, there's no manual calculations. It's all about interpreting the graph. I'll show several ways to construct and interpret the graph. I've also made a plug-and-play software tool for that. Upload your data and it will give you the equivalence point within seconds. You can find the spreadsheet and software linked in the video description. If you have any trouble accessing it, leave a comment. I'll make sure to get you a copy. Second, our experimental data isn't perfect. Our calculated values should reflect the precision of our measurements. I am talking about the significant figures and uncertainties of our data. The proper way would be to calculate the correct significant figures, then to calculate the total uncertainty, and when we express our results, it itself would have a significant figure count and an uncertainty associated with it. This topic deserves a whole video of its own, so I will simply perform the calculations with respect to significant figures. That is good enough for what we are doing. Let's dive into the calculations. First, we will calculate the theoretical molarity of the sodium hydroxide solution we prepared. We will start with the mass that we measured of sodium hydroxide. So that was 4.02 grams of sodium hydroxide. Now, we are using the molar mass up here, which is 39.997 for sodium hydroxide. So 1 mole is 39.997 grams. When we punch that in our calculator, we will get 0.100508 moles. Now, because of significant figures, we only have 3 significant figures. If we were to express this, this would be 0.101 mole. This is how many moles of sodium hydroxide we have. Then we'll calculate the molarity of the solution that we prepared. So the solution volume was 1 liter. And for significant figure's sake, because we're not using uncertainties, we're going to say this is exact. I think in reality it was like plus and minus 0.60 ml, I think. But we're not using that. We're going to say this is exact to keep significant figure calculations consistent here. So now we have 0.1005 moles over 1 liter exactly. That will result in 0.1005 molar solution. Now, if we recall significant figures, that's that and that's that. I used an extra digit for the calculations, but we do not express that extra digit. So this, if we were to express this on its own, would be 0.1001 molar. That would be our result. This is the theoretical. Right? because the whole point of this titration is to determine the exact molarity, not the theoretical. So this is the theoretical. All right, now we're going to calculate the molarity of the KHP solution. So we're going to use the same logic here. We're going to start with the mass, which was 10.22 grams of KHP. Now, again, using the molar mass over here, this is actually only good to the second place, so these two digits are not significant. That brings us to 1 mole is 204.22 grams. Grams cancel out here again. That will result in 0.050044 mole. But we only have 4 significant figures here, so that's where it ends. If we were to express this on its own, that would mean it would be 0.05004 moles. All right, so now we're going to calculate the molarity of the KHP solution. So the volume was 500 milliliters and exactly. That is 0.5 liters exactly. So that means we have 0.050044 moles over 0.5 liters. That makes the solution molarity 0.1009 molar. Now, if we were to express this on its own, that would be 0.1001 molar. So we overshot it slightly, but it's not a problem because we're going to be calculating it anyway. So now let's fill in our sheet here with the values that we just calculated. So the molarity of the KHP solution will be 0.1001. And our moles of KHP and all these other we'll calculate now. So now in a separate sheet, I'll calculate the trial run molarities. So for trial 1, we will first have to calculate the moles of potassium hydrogen phthalate, or KHP. We started with 20.0 mLs of KHP solution. And that was, let's not forget, we just calculated 0.10009 molar. We're going to use this unrounded version for our calculations, and we'll round these significant digits at the end. So 20.0 ml is equal to 0.0200 liters. To get the total moles, we multiply the volume by the molarity. So 0.10009 moles over 1 liter. Remember, that's exact. Now, you don't have to do it exact like this. You could just multiply these two, but to show you, that is 2.0018 times 10 to the negative 3, or 0.002018 moles. If we were to express this on its own, again, this would be 0.00200 moles, because we only have 3 significant figures here, so that's 3 significant figures there. Now let's fill in our sheet, and I'll use the unrounded scientific notation, so it fits nicely here. So that'd be 2.02 times 10 to the negative 3. Now for the total titrant delivered is simply the endpoint minus the initial, which gives us 20.2. Since this reaction is 1-to-1, the moles of KHP equal the moles of sodium hydroxide. We had 0.00202 moles in 0.02020 liters. That's equal to 0.099109 molar, which is approximately 0.0991 molar. This is our final answer with respect to significant figures. So if we were to fill this in, it would be 0.0991 molar. Like I mentioned during the titration, I'm pretty sure I went slightly over the endpoint. It is not a problem in our case since we will use the pH curve, and this titration was to determine roughly the endpoint. However, this method can be really accurate. Just titrate carefully and perform several runs and average the results, and you should get a really close answer to the reality. This, in our case, I'm using it as the gauge to know when to start our fine step. Now let's move on to the potentiometric titration. I'll first start by transferring all this data onto the computer and we'll take it from there. So now that we're on the computer, I will show you the titration record sheets. So here we are in the shared folder. This is in the video description. This is a Google Drive folder. There's all of this stuff and more in this folder. So if you go to the blank titration record sheets, you can see this is the indicator titration sheet, and this is the potentiometric titration sheet. You can make a copy of these for yourself by going to File and saying Make a Copy, or you can download it as a Microsoft Excel. There's many formats here already available for a quick download. On this sheet, if you fill in the mass of potassium hydrogen phthalate solids and the total volume that you diluted it to, it will give you the molarity of the solution. And based on that, it will calculate the molarity of sodium hydroxide solution. For that, you need to fill in the aliquot volume of potassium hydrogen phthalate solution. With this, it will calculate the moles of potassium hydrogen phthalate. You'll fill in the initial burette reading and the endpoint reading. It will calculate the titrant volume delivered. And as a result, it will calculate the molarity of the sodium hydroxide solution. This was the manual calculation that we just performed. Over here on the potentiometric sheet, this doesn't do any calculations. This is purely for you to organize the data. Over here, I have a filled out version of these. So as you can see here, this is our experimental data. And over here, we have our potentiometric titration data. Now, to make it a little bit easier to make a graph, I have simply copied and pasted all this data into single columns. So here we have milliliters of sodium hydroxide and the resulting pH. From this, I simply made a chart. From this chart, as you can see, these are all of our data points. And our Excel fills in, creates a line in between to create this smooth curve. If it was just the data, you just see simply points. But as you can see, our smooth titration curve. This is why we took many samples right around the endpoint volume. As you can see, the curvature really starts to change rapidly. That's why we needed many data points to be able to get this section clearly. As you can see down here by the tail, it doesn't matter as much, and it doesn't matter as much up here as well. So this is how the graph on the spreadsheet looks. This may be good enough for your purposes. As you can see here, the 20 milliliter line is very, very close visually to the inflection point. Probably for our application, this would have been enough, but I decided to explore it deeper. Let's go back to our drive. You will see this file. And in here, there's a Python script that you will load your CSV data in. This is simply all the data from here, the two columns. And the Python script uses that to construct a graph. This is the instructions on how to use it. Please check it out. It's very easy. So if you go back, this is my results from running the Python script. So this is what interests us. As you can see, these blue dots are our data points, and the orange line is a best fit function. Now, I'm not going to go into detail. You can check it out on the instructions, but it's finding the equivalence point and the equivalence pH. We're, for our purposes, only interested in the equivalence volume, so 19.972 milliliters, and we will use that to determine the molarity of the solution. Now, if you recall, we did the manual calculation, and we got the same result as we did here. So we can use this spreadsheet to also do the calculation for us. So just make life a little bit easier. So here, I've downloaded the spreadsheet. You can make a copy for yourself as well. We used 20 milliliters again, and I'm going to say the initial was 0, and the equivalence point was 19.972. It's going to see there, and it calculated the molarity for us. As you can see, our theoretical molarity and our actual molarity are very, very close. It appears we have created a slightly more concentrated solution, but for our application, this is perfectly okay. And knowing this, we can correct any calculations moving forward. So then when we titrate with the sodium hydroxide solution, we can use this value here. I really, really like this graph. This is very easy. You just plug it into the software and it will give you this directly. And this will work for any titration curve, really. It doesn't have to be a sodium hydroxide and KHP. I'd like to show you another way to get the same answer. So on Desmos, you can plug in your points, and I'll show you how to do that. So if we just copy and paste these values, you will get the data points. And if you use this general form here, and then add a slider for all, you can adjust the function to visually match. So I'm going to think the other one was like about 5 for this. And then we can adjust M to move it up, and then B to move it sideways. We don't have enough here. Let's say, I know it's going to be somewhere around 20, so let's do like 22. And let's make this from 15. So we have a little bit more fine tuning here. So here we can move it to right about there. We can multiply that. Well, see how a little bit of change is really dramatic. So 0.2 is too much and 0 is not enough. So what I'm going to do is change this to 0.1 to 0.3. And as you can see, oh, wrong direction. So I'm going to do 0. Here we go. So you can see we're getting very, very close. Now I don't like how little range we have here. So I'm going to say this is going to go from 8 to 9. See, that definitely gives us enough range. And then if we multiply a little bit more. Now zooming in to right about the equivalence point, we can adjust this even more. So that looks very close to our curve, correct? Unfortunately, because titration does not have to follow this general form, it's not going to be perfect. but we can get a very, very, very good estimate. Now, as you can see, the B will be our milliliters because that's offsetting the x-axis, and the M will be our y-axis, which is going to be our pH. So our pH here is 8.475, and our milliliters is 19.96. Now, if we go back to this, that is very, very close to that value. And, you know, depending on your comfort level with stuff, this may be easier. Both methods work. This is a little bit easier in my opinion if you're comfortable with just, you know, following instructions. This is, you know, also, I like this because it's kind of, you know, a little bit of a mathematical approach too. It gives you a little bit of math understanding as well. This concludes the calculation part of our lab. We have successfully prepared and standardized our sodium hydroxide solution. Now it's ready for any application where an accurately known base is needed. Please share your thoughts and comments, and thank you very much for watching.